In this section, we're going to start studying some of the applications of nuclear chemistry. The first thing we're going to talk about is, well, how do you actually measure the activity of these radioactive isotopes? Remember, most of them exist in very, very small amounts. Very small percentage of the samples of elements are actually radioactive isotopes. They are, however, very high energy, so we have methods for detecting this. So let's start out by discussing how we measure radioactivity. The unit of measuring radioactivity is called a becquerel, abbreviated BQ, and this represents 1 nuclear disintegration per second. As you can imagine, that's hard to detect, and so more commonly we use the unit of the Curie, Ci, which represents 3.70 times 10 to the 10th becquerels. This is essentially the rate of decay of 1 gram of radium. This is still a very large number of disintegrations or decay events per second, so it's more common to work in the range of the millicuries or MCI. Now, how do we detect this radioactivity? One of the most common methods is by, for example, the ability of the energy of these events to expose some kind of photographic film. So because the particles emitted by radioactive nuclei have a lot of energy, even though they're in small amounts, we can detect them because the rays or the radiation can expose photographic film. And this is why people who work in industries where they're exposed to considerable amounts of radioactivity, besides the protective clothing that they wear, they also carry with them these so-called film badge dosimeters. Sometimes they wear them as a badge, sometimes as a ring, and periodically the badges and the rings are checked to see how much radiation the worker has been exposed to and make sure that there is no danger. This is a sketch of what's called a Geiger counter, more commonly known as a Geiger counter. Notice that it consists of a tube that has argon gas in it and a window on one end and essentially an open circuit inside. There's a bar in the middle called the anode, and the rest of the body of the tube consists of the cathode. We'll learn more about this terminology later on. Suffice it to say the cathode and the anode are the two terminals, the two electrodes that when the circuit is closed, it allows electrons to be transferred and generate a current. Remember, argon gas is an inert gas. It doesn't ionize very readily unless it picks up enough radiation through the window to ionize the argon gas. And once that happens, it allows electrons to be transferred between the cathode and the anode. And that is detected by an amplifier and counter that you see here on the left. The voltage has already been established by a battery to allow that as soon as the argon gas becomes ionized, a current can start. Now, this is a small current, so it has to be amplified, right? And sometimes the way you amplify it is by generating sound, for example, like a clicking sound. You've seen this in movies probably, or a flashing light, or you can connect it to a display, either analog or digital, and have a readout of the actual amount of radiation that's being detected. Now this is a sketch, so you can have Geiger counters in different modes. The one you're probably more familiar with is this one, where the tube carried in the hand is the one you point towards the source of reactivity, and you can see there a analog display of the radioactivity. Nowadays we have some handheld pocket-sized devices that do the same thing. Now one thing to take into account here is that typically, remember, 1 Curie is essentially 2.22 times 10 to the 12th disintegration events per minute. Because these instruments will have a certain measure of inaccuracy in it, we typically adjust it and compensate. And so when we report the units, we actually report more like CPM, which would be counts per minute. This is an adjustment to the actual disintegrations per minute, dPm, And that's really what you can see here. If you have this in your PowerPoint notes, you might want to zoom in, kind of like magnify this, and you can see the scales here that say CPM. And that is more commonly the way we deal with it in the lab. Another way of measuring reactivity has to do with samples that do not have sufficient activity. In other words, these are isotopes that emit radiation that is not sufficient to ionize like argon or air in a simple Geiger counter. For example, tritium, the majorly used isotope of hydrogen, is a very low energy beta emitter. So what you can do is you submerge your sample in a substance, it's called a scintillator, that fluoresces, in other words, that takes that energy and re-emits it in the form of visible light when it's ionized. And so this fluorescence can be amplified and detected in the counter. So for example, in this case, you have the machine here on the right. This is probably an older version. You can tell by the picture of the computer and the dot matrix printer in the bottom left. But anyway, the idea is that the samples are put in little vials, typically plastic or glass vials, and they're placed in this little conveyor belt of spaces that rolls around. And as it goes around, these samples are all submerged in this scintillator, and they are detected by the computer, or you can print the activity of each one of the samples. Now, actually, there is a way you can do the same thing without using a scintillator. For example, the isotope phosphorus 32, P32, is a high energy beta emitter. So in this case, you can actually count the activity without having to put a scintillator fluid in there. This is because the radiation from the phosphorus isotope ionizes air particles and actually generates kind of like a bluish kind of light. This is called Cherenkov radiation, and this is this is what causes the kind of like bluish kind of glow that one can see if one could peek inside a nuclear reactor. Now, notice all the units we've talked about here. We've talked about something per second or something per minute. So anytime you see any unit that has those kinds of subunits in them, of course, we think about kinetics. So let's talk about the kinetics of radioactive decay. This is going to be very similar to what we studied before with chemical reactions, with a few differences in the case of nuclear reactions. So remember, in this case, we call the starting material, we call it the parent nuclide, and then the product, we call it the daughter nuclide. It turns out that the rate of radioactive decay is first order. So the rate consists of the product of lambda times n, and of course we can do the integrated form of this in the form of natural logarithm of nt over n0 equals minus lambda t. Now what are these things? Well, n would be the number of atoms at a certain time t, and we say the number of atoms would mean the number of radioactive nuclides still left at that time t. And then n sub 0 would be the number of atoms, in this case, of course, radioactive nuclides at the starting time, t equals 0. Lambda is called the decay constant. It is parallel to what we call K, the rate constant in chemical reactions. And because this is a first order process, we can define the half-life as the natural log of 2 over the decay constant, so 0.693 over lambda. In other words, this is the time that it takes for a sample of a radioactive isotope to drop to half of its original activity. Okay? All right. So let's go ahead and look at a sample of something very interesting here. It turns out that many radioactive isotopes don't just go through one disintegration step. Many of them go through various steps. And in this case, we have what is called a radioactive decay series. For example, the very famous uranium isotope U-238, which is used in many of the applications for generating nuclear energy, as you can see here, it goes through several steps. Some of those involve alpha particle production, some of them involve beta particle production, and you can see that the final product of the whole series is lead-206. You can see here. So we would say that the uranium-238 is the parent, and then we could say that for any one of those steps, the product is the daughter nuclide, or we could say that the whole series ends up in lead-206 as being the daughter nuclide. Now, remember, like we studied before when we studied reaction mechanisms in chemical reactions, in nuclear reactions of this kind, there is an analogy in that sometimes there is one step that is a longer, slower, in other words, has a longer half-life, and typically, many times, that step is the one that determines the half-life for the whole process. Of course, remember in this case, these are events that have to do with the decomposition of each one of these individual guys. So essentially, we have to be careful not to draw too many parallels with chemical reactions. Now, the cool thing about using half-life is that sometimes you can count the decay of things in a number of half-lives. Let's do a little practice here. Strontium-90 is a radioactive isotope with a half-life of 28.9 years. So, for example, you could start with a certain amount, a certain activity of strontium-90, and you could go here and see what would be the resulting amount left after each half-life. So if each half-life is roughly about 28.9 years, you can see how after each half-life you have 1/2 of the original amount. So if you started with, let's say, 10.0 grams, after one half-life you have 5, after two half-lives 2.5, to three half-lives, etc., 1.25, etc., etc. So you can see how we've done this before, so it's a way of counting. So in this case, we're going to calculate how long in years it will take for 1.00 grams of the isotope to be reduced to 0.200 grams by decay. So let's go to our screen set here, our document scanner here, to solve this problem. This is essentially a kinetics problem similar to the ones that we solved in the previous unit. So let's start out by writing what is the integrated rate law equation, or the equivalent here in this case, the integrated decay rate law. So we would say that this is log of A final over A initial, or we could say, instead of A, let's say we say N, say we say N here, and this is minus lambda D. Remember, whatever numbers we decide to put in here, anything we put in here is going to cancel out. In other words, N is the number of atoms, right? Now, what they're giving us is grams. But remember, you can convert from grams of strontium to numbers of atoms of strontium, right, using the molar mass and Avogadro's number. But remember, this is a ratio of the same thing. All of those conversion factors are going to cancel out anyway. So as long as we use the same units on the top as we do in the bottom, it really doesn't matter. So we can say simply this is going to be the mass of one versus the other. Okay, so they give us the value of the half-life, and what we need to do is use the value of the half-life to find what is the value of lambda, the decay constant. Remember we said that T1/2 for a first order rate reaction is 0.693 divided by the constant, which in this case is lambda. That means that lambda equals 0.693 divided by the half-life. And that one's given for us here. So 0.693 divided by the half-life, which is 28.9 years. We can do the math here, and it would give us 0.0239, and the units here would be over years. So we can write that as years to the -1. So now we have a value of lambda. They're telling us what is the initial amount of strontium-90. They want us to calculate what is going to be the time to get to the final amount of strontium. And so all we have to do is solve for T. So now we're going to solve for T. So let's say we're going to say, okay, so log of the final amount we're looking at is 0.200 grams divided by the initial amount, which was 1.00 grams. And again, since both of these are grams, we can convert each one to numbers of atoms, but those conversion factors are all going to cancel out. And now we have minus lambda. We said lambda is 0.0239. Don't forget always to put the units in here, all right? Because it's important that the units cancel out properly. Times T, which is our unknown. So if we plug in, these numbers in here and do our math, we find T equals 67.3 years, accounting for the proper numbers of sig figs that we've had so far here in all of these calculations. Okay, thank you very much. Because we know the half-lives of some very specific isotopes, in particularly those that consists of elements that are specific to certain forms of substances, one of the most important applications of nuclear chemistry is what we call radiocarbon dating and other forms of dating samples based on the decay of known isotopes. For example, we know that carbon-14 is a beta emitter that decays to form nitrogen-14. And in this process also, by the way, this has a half-life of 5,730 years. In other words, the half-life of carbon-14 kind of covers all of the period of human history. And therefore, by measuring the presence of certain amounts of carbon-14 in a given sample of organic material, let's say wood or bones or things like that, we can pretty much use the half-life of C14 to calculate how old that specimen is. Now, if we want to go to longer spans of time, we might use uranium-238. So remember I showed you the series, the radioactive decay series of uranium-238 all the way down to lead-206. In the process, 8 alpha particles and 6 beta particles are emitted. The half-life of this process is about 4.5 billion years. In other words, this spans kind of like the period of our Earth's history, so to speak. In other words, how old the Earth is. And so we could use this to detect or to calculate the age of samples of, let's say, rocks or different kinds of minerals. The process requires a little bit of thinking, so let's go ahead and do a practice exercise here, which is typically done. This is using C14. So the example reads, charcoal samples taken at Stonehenge, England have a C14 specific activity of 9.50 dpm, disintegrations per minute, per gram of carbon. Living wood in the area has a specific activity of 15.3 dpm per gram. If the half-life of C14 is 5,730 years, how long ago was the charcoal part of a living plant? Let's go ahead and solve this problem in our document scanner.
This is a typical example of a problem relating to radiocarbon dating, and specifically in this case, some samples taken from a important archaeological site, Stonehenge. Notice that we're comparing the activity of charcoal samples with living wood. Don't forget, our idea here is that a radioactive isotope decays on a first order kinetics type of process. Carbon 14 is useful because it is an ingredient of organic material, specifically living material. Notice that we're comparing charcoal, which means this is, so to speak, dead wood. This is wood that is no longer living, is no longer active. In other words, it is not undergoing the metabolic reactions that would cause it to incorporate carbon 14 into its cells as living wood would do. Excuse me. So when we compare the number of atoms here at the end versus initial, once more, like we said before, it doesn't matter what we put in there, because anything we put in there is going to be converted back into numbers of atoms using the same conversion factors. So essentially what we're saying is that we could write this as the call this the activity. Let's call this C14 that we have at this point, and the C14 activity that we had in the beginning. And this is again minus lambda T, where lambda is the decay constant. Notice that if wood is living now and essentially active metabolically, it will be incorporating a certain amount of carbon, and so the activity of that living wood represents, well, this is how much C14 is available at this point in time. The charcoal has a different activity because it represents the decay from the last time that that charcoal was a living plant and was incorporating C14. And this may have been a long time ago, and so the activity we detect in that charcoal sample represents the C14 that was present when that charcoal was part of a living plant, hundreds or thousands of years ago, and at that point stopped incorporating C14. So whatever C14 is in there is the result of the decay of the original one. Okay, so the first thing we need to do is, well, how long did it take for it to get there? In other words, we're going to solve for T, the time that it took. To do that, we need to know the value of the decay constant. But don't forget, we said that if T1/2, the half-life, is 5,730 years, that should be the log of 2, 0.693, divided by the decay constant. This is true of first order kinetics. And so we can solve for lambda, and we can rearrange this and find out that lambda is to 3 significant figures, right? It would be, let's say, 1.21 times 10 to the negative 4 per year, the typical unit of a first order constant. So now that we have that, we can plug this number in here and say, well, let's say the C14 was incorporated at a time, and since then its activity has decayed to 9.50 dpm, or disintegrations per minute. But if it were alive right now, it would have 15.3 disintegrations per minute. And that should be representative of what that amount of C14 was there, whenever that happened. Notice that we do have to make some assumptions here, and I'm sure as a good scientist you should be questioning these things, but these are things that have been practiced for many, many years, many decades, and so you can research the literature if you have concerns about the validity of this approach, okay? So we're going to say this is going to be minus lambda, which we just said is 1.21 times 10 to the minus 4 inverse years, and that'll be times t, the time, and we're trying to find out, well, what is t? In other words, how long did it take for that C14 to decay from the level it would have been if it were living still to the level that it was when it stopped being a living organism, right? In other words, it has decayed from that time. It should have been 15.3, but this is representative of, well, back when it was alive, it would have had 15.3. Now it only has 9.50 dpms of activity. So we can solve for this. And I guess, accounting for sig figs and all that kind of stuff, we will get 3,940 years. All right, so that is the solution of the problem. And this is an example of one of the methods that are used to obtain the dates or the age of samples, in this case in particular organic samples, samples that are known to incorporate carbon-14 isotope when they are active. Thank you very much.
So far, we have been studying nuclear chemistry of naturally occurring radioactive isotopes, C14, H3 or tritium, uranium-238. However, since ancient times, people have dreamed of converting one element into another, especially in the Middle Ages. People went around trying to find ways of converting common metals to gold. Well, it turns out in 1919, Rutherford, the scientist who gave us the model of the atom that we discussed at the beginning of this unit, carried out a reaction where he bombarded nitrogen atoms with alpha particles, and as a result, they converted nitrogen into oxygen-17. This phenomenon is called nuclear transmutation. So, literally the conversion of one nuclide into another one, or one element into another one. Let's look at some other examples. For example, you can also convert aluminum to phosphorus-30. You can convert nitrogen itself to carbon-11. Notice that in these processes, you are essentially bombarding the target element with particles, let's say alpha particles. And in the process, not only do you create a new element, but you also generate other particles sometimes, protons, neutrons, etc. Now, neutrons don't have a charge, and so they're not going to be repelled easily by the nuclei of the target element. So they don't need to travel at such high speeds that when they hit the target, they don't have enough kinetic energy. On the other hand, alpha particles and protons have a charge. So when they are, thrown against a nucleus, there's going to be some repulsion from the positive charges of protons in the nucleus. So in order for these collisions to happen with sufficient kinetic energy, we have to accelerate the bombarding particles to tremendously high speeds. And this is done with what's called a particle accelerator. Let me show. This is just a sketch again. What you have is you have like a circular circuit, so to speak, or channel with an alternating voltage that creates a magnetic field. And so your bombarding particles, protons or alpha particles, are generated and accelerated to this process at a very high speed until they hit their target. This one in particular is a circular particle accelerator or a cyclotron. There are also linear accelerators. Let me show you a picture here. This is a very famous one. This is the Large Hadron Collider. This is near Geneva, and it has a circumference of somewhere around 27 kilometers, like 16 to 17 miles. Very famous particle accelerator. All right. So when you do a transmutation reaction, there is a shorthand notation for it that consists in writing first the parent nuclide, and then in parentheses the colliding particle, comma, the particle that is emitted, and then close the parenthesis, and then the daughter nuclei. All right. So, for example, when you see this symbol here, notice that it starts with iron 56, and then you have parenthesis D, comma, alpha. Close the parenthesis, and you have manganese 54. Well, what that represents, the reaction, is the iron 56 is the parent nuclide, so you can see it there. D is kind of like a shorthand symbol for this isotope of hydrogen, which is commonly called deuterium. All right, let me see if I can get my pencil to write here. So this is called deuterium, D-E-U-T, deuterium. That looks like something my 4-year-old granddaughter wrote, but I'm sorry, I'm not very skilled at writing on screens like this. This is a very commonly known isotope of hydrogen, deuterium, H2, and that is the colliding particle. And then you have next, right, you have the emitted particle. You can see it here. It's an alpha particle, and so we're writing it here as one of the products. And then finally, the daughter nuclide, which is the manganese 54. You can see it there. Okay, so this is a shorthand notation to represent this reaction. So let's do this. It's a little practice one. Write a balanced equation for the following nuclear transmutation. All right, let's go to our document scanner for this.
In this exercise, we're going to write the nuclear equation that corresponds to this notation for a transmutation reaction. Let's zoom in a little bit here so we can see it a little better. So what we're seeing here is it's telling us that the parent nuclide is this entity here, right? So this is my parent. And over here on the extreme right, we have silver 109, and that is our daughter nuclide. Let me go back in here again. Okay, this is our daughter nuclide. Okay, don't worry, I'll zoom back in again. In parentheses, we have what is the colliding particle. So this is over here, alpha is our colliding particle. And then the other entity inside the parenthesis is the emitted particle. So what this equation is telling us is that we're going to start with an atom of palladium 106. We are going to collide in an alpha particle, and the result is going to be the emission of a proton, and the resulting daughter nuclide is going to be silver 109. So let's write that out. Let me zoom back out here so we can see everything that's in there. So let's convert this notation into an equation. So we would have, first of all, palladium. And it says here that this is 46 atomic number. And this is the 106 isotope. We're going to collide it with an alpha particle. And I told you that we can write that in different ways. I like to think as alpha just because I like to write Greek letters. So there is our alpha particle. And this is going to generate a proton, which remember we write in the form P with a atomic number or nuclear charge of 1 and a mass number of 1. And remember, this is small p, this is not large, capital P like in phosphorus. And the other thing we're going to generate is we're going to generate a silver 109. And the atomic number is 47. Okay, before we close it off, let's make sure this is balanced. So across the top, on the left, we have 106 plus 4. That's 110. And over here, we have 109 plus 1. That's 110. So that's balanced for the mass numbers. And then on the bottom, 46 plus 2 is 48. And over here, 1 plus 47 is 48 also. So we are balanced in terms of the nuclear charge or atomic numbers. All right, that's how you interpret this shorthand notation of a transmutation reaction and convert it into the balanced nuclear equation.
As this table shows us, there are many different elements on the periodic table that are not found in nature. They have actually been created by this process of nuclear transmutation. And you can see some of them in there, like neptunium, plutonium, you can see californium, curium. And notice that all of these, some of these have been done with neutron bombardment, some of them with positive ion bombardments like alpha particles, or even other atoms of other elements. And you can see the different products or daughter nuclides and the half-lives. So very interesting. For example, plutonium, which is a very important component of many nuclear energy applications, etc., etc. So just so you know, there are many elements on the periodic table that have been generated this way. These are some of the more stable ones. Some of them have barely been observed for a fraction of a second, perhaps, or so.